Hi guys, it's Mrs. Moss here, and we've been learning about weathering. Now it's time to talk about erosion. Very often you confuse the terms weathering and erosion. They're very two different processes, but they do go together often, which is why I think there's confusion. So if you think of it like this, weathering is the prerequisite for erosion. That means weathering has to come first before erosion can occur. So rocks have to be broken down before they can be eroded away. And erosion is just simply the transport of sediments from one location to another. Okay? So weathering is the breaking down of the rock, and erosion is the moving of that rock. Here we have a diagram of the Montauk Lighthouse. Now some of you may have visited that at the end of Long Island. In 1838, you could see the amount of land that was next to the lighthouse. Well, over time, since over 200 years, it's lost about 200 feet of that land because it has been weathered and eroded. Let's talk about erosion and what causes erosion to occur. It's really driven by the force of gravity. Avalanches and landslides are both examples of that, how the gravity works and the force of nature of gravity works against the land and it literally pushes it down. Here's another example of landslides that occur because of gravity. Now there are certain agents of erosion that you're going to be responsible for, and there are 5. The agents of erosion are, or the ways that erosion can happen are by water, like streams, rivers, and oceans, ice, moving glaciers, wind, or the atmosphere, gravity, like avalanches and landslides, like I showed you pictures of, and Earth's processes, like earthquakes and volcanoes, plate tectonics, shifting. So those are what we're going to be looking at a little more in depth in the next few slides. Now, each agent of erosion produces its own characteristic or shape in the rock. So you can notice from running water, the rocks here from this diagram are smooth and round. Here, the glacial ice has created scratches or striations in the rock, and that's indicative of that it had been moved by glaciers. Wind, you'll notice that it creates a slanted formation or shape in a rock, and gravity will tend to just pull that land down or that rock down, and it creates more of a jagged rock. So if you don't have a printout of these notes, I would definitely take the moment and copy down the picture of each of these diagrams. So how does running water cause erosion? We're going to look at the first one on the list because running water is the primary agent of erosion. Here's a beautiful picture of the Grand Canyon. Now this actually was formed by the Colorado River and the running water that carved it out over millions of years. So running water will round and smooth the rock. It makes the rock smaller because the jagged edges then get broken off. Here's just a picture of running water over rocks. It kind of gives you a good visual of how running water can smooth out and carve and round a rock. Now, again, erosion by water, the particles are carried in several different ways depending on their size. So you could imagine the heavier, bit larger a rock will be, the difficult or the slow nature of the movement. So let's take a look at this. There's 3 ways streams can transport materials. The first one is by solution. The sediments are dissolved like salt ions. They're not really visible, but they're carried by water. The second is through suspension. And if you know what the word suspension means, meaning like if something is suspended in air, it's kind of floating, right? So with suspension, the sediments are floating in the water and then carried down that way. And we see this with sediments like clay or colloids, silt, and sand, some of the finer particles that we've looked at. The last way is by saltation, which is literally just rolling or bouncing or dragging along the bottom of the water. Those would be more like the pebbles and cobbles. Now here's just a picture of how sediments move, and it's a diagram of what I was just talking about. The smaller particles are dissolved or they're suspended, and that's the clays, the silts, the smaller particles. And then we have the larger particles like the cobbles and pebbles and boulders that will get dragged along the bottom as it moves. Now the larger sediments will be rolled, or like I said, dragged. Now this will lead us to the reference table. And we've seen this before. We saw it in terms of when we were learning about rocks and their sediment sizes that can create sedimentary rocks. We're going to look at it again now, and we're going to look at the component at the bottom, which we haven't looked at yet, which is stream velocity. Now this tells us how fast a stream needs to be moving in order to carry these size sediments. So let's give you just some examples of how we would use this reference table on a test or a quiz, or just use it practically. Calculate the minimum velocity of a stream needed to carry a pebble. Well, if we're going to think about pebbles, we know that they're the very least smallest part of a pebble will be 0.2. So we're going to have to go over to 0.2 on the pebble side of the sediment chart, and we'll go down until we see that the stream velocity reaches 10. So that means the minimum speed that a stream needs to move is 10 centimeters per second in order to carry the smallest pebble. Let's do another one. What is the minimum velocity needed to carry a boulder? Well, again, we're going to need to go over to the boulder, to the smallest part, the 25.6, and we see it reaches the black line right at this point. We go up, or you could go down. The scale is the same from the top to the bottom. When you go up to the top and you're working with boulders and cobbles, it's just a little bit easier to use the scale that's up here. It does match the scale that's below. So if I know that this line is 100, that means the boulder, the minimum velocity needed to carry this boulder would be 200 centimeters per second. Let's look at yet another one. What is the largest particle size particle that can be carried by a stream flowing 400 centimeters per second? Now the answer is boulder, and we see that because 400 centimeters per second is following this red line, which indicates that it would be boulders. Anything to the right of this black line can be carried by the water. Now, if a stream is flowing at 150 centimeters per second, what is the largest sediment it can carry? So we go up from 150 centimeters per second, and we go over, and we see that the answer is pebbles. Name all of the sediments a stream can carry if it is flowing 5 centimeters per second. So we go to 5 centimeters per second, and we see that it's going over to sand. This means that the stream can carry, when it's moving at 5 centimeters per second, it can carry sand, silt, and clay. So we go from the bottom up to this black line and over. And anything that's below it is small enough to be carried along with the uppermost size particle that it can carry. Don't worry, we'll get a lot of practice in class. Now, how does a stream velocity affect erosion? The velocity of the stream depends on the slope, or the gradient of the stream, and it also depends on the discharge, or the volume of water. Let's go back. A flat gradient will produce slow-moving water, and a steeper slope will have faster-moving water. That makes sense. In a straight stream, the velocity of the stream is fastest in the middle due to less friction. So if you look at this person that's in the middle here is really experiencing the rapids because the movement of the water is faster in the middle than on the edge of the bank where the water is brushing up against the bank of the river. So it's the friction that's being caused there is causing the water to slow down on the edges in a straight stream. Now this is demonstrated by this diagram. If you look here, this is the stream bottom. Okay, so we go from one side of the river. If we were walking, we would go in, and it would get deeper and deeper as we go, and then as we get across to the other side, it gets shallow again. This is a straight stream. So if we were in this stream, the fastest water would be moving in the middle towards the top, just below the surface. That's where the erosion is occurring at the fastest rate. We have a difference when we see meandering streams. Meandering streams are curvy streams, and the erosion will occur on the outside curve. And that's when the water is gaining the most speed. So in a meandering stream, we have an outside edge and we have an inside edge. And you can see there's a white strip of sand along the inside edge. Well, the outside edge is pulling that water and moving it faster around the curve. That's where the erosion is occurring in this meandering stream. So the fastest water goes and erodes the banks, and it makes the curve even larger. And as rivers flow and streams flow, they carve out V-shaped valleys. So check this out. You can really see over time, and this is of course thousands and thousands of years, but over time they carve out these V-shaped valleys. And you can remember that because river has a V in it. V-shaped valley, river. And here's another picture of a V-shaped valley that was formed by a river. So, a summary of water erosion. Running water is the most powerful erosion on Earth. It is smooth and it smooths and it rounds out rocks and deposits them according to size. We're going to get to that a little bit in another video. The faster the water is moving, the more erosion can occur, and the rivers are carved out into V-shaped valleys. We're going to end this part of erosion now, and we'll go back and learn a little bit more about the other agents of erosion in another video. Hope you have a great day. See you next time.